This conference will now be recorded.
All right, this is Math 211, Section 2.8, Part 2. I had a few extra examples I didn't get to finish in the last video. We're looking at related rates and just varieties of different types of examples. So this one is a plane is flying horizontally at an altitude of 1 mile. So remember, altitude is the height from the ground, and a speed of 570 miles per hour, and it passes directly over a radar station. So we kind of go ahead and draw a few things. So here's my radar station. We know that if we go up, and that is not a straight line, but you get the gist. If we go up 1 mile in the air, and then we know the plane has already passed here, so we're assuming the plane is somewhere further along. So this is a fixed number. The plane is flying consistently at that 1 mile altitude. So we kind of have a Pythagorean theorem here. It looks like right triangle. Let's call the distance between when the radar and the plane met x, and the distance between the radar station and the plane's distance, the actual distance, y, because this is how far it was that it passed over it. This is how far these two things are from each other. So it says that the plane was flying at 570 miles per hour. So that means the change in x over change in time, so dx dt, is 570 miles per hour. That's our rate. And then we're going to be looking at a specific scenario where the plane, what we're looking for the rate at the distance that the plane station is increasing. So we're looking for dy dt, the distance between them, how is that changing when it is 2 miles away from its location. So we're going to consider for a minute what if y was 2. So if we plug that in, that would make this able to find x in that specific instance. So it's 2 squared equals x squared plus 1 squared, because that's our hypotenuse is y. So that's 4 equals x squared plus 1, so x squared equals 3, or x equals square root of 3. Okay, so now to talk about this in terms of changes of rates, we need to again write the formula that it is x squared plus 1 squared, which is 1, equals y squared. That is our formula that connects all of the pieces together. It's the Pythagorean theorem. If we take a derivative with that with respect to x, or excuse me, to t, because we're doing time, we're going to get 2x dx dt plus 0, because that's a constant, and then 2y dy dt. Now we're trying to solve for dy dt, so we can divide over that 2y. So that actually ends up being x over y dx dt, because the 2's would cancel out, equals dy dt. Now let's plug in what we know at that specific instance. We know that x is the square root of 3. We know at that moment in time y is 2, and that the speed that the plane was traveling, dx dt, was 570 miles per hour. So that would give us our dy dt, which is the change in distance over time for those two things. So let me get my calculator. 570 cut in half, and then we're going to times it by the square root of 3. So this one ends up being 285 square root of 3. And if we times that out, sorry, my calculator is being a little funny. That's 494 if we round to the nearest whole. And that would be our miles per hour. Because remember, this is change in distance over time for the increase. All right. So we're going to be looking at example 9 next. Sorry. It says Boyle's law states that when a sample of gas is compressed at a constant temperature, the pressure P and the volume V satisfy the equation PV equals C, where C is a constant. Suppose that at a certain instant the volume is 700 cubic centimeters. The pressure is 200 kPa, and the pressure is increasing at a rate of 20 kPa per minute. At what rate is the volume decreasing in that instant? So we're talking about volume. So we need to make sure that we use our formula that they've given us that relates the pressure, the volume, and the constant C. Notice that is important that C is a constant, so that when we take the derivative in a minute, that's going to be a 0. So if we take the derivative with respect to time of this, that's going to be, this is going to be a product rule on this side. So it's going to be first times derivative of the second with respect to time, plus the second times the derivative of the first, again with respect to time, equals 0 since the derivative of a constant is 0. We could solve this for change in volume, which is what we're looking for. So that would be dv dt. So we'll subtract over the negative v dp dt, and we'll divide by p. So it ends up being negative v over p times dp dt. And then they gave us some specific information. They told us at that specific moment the volume was 700 cubic meters. So that would be negative 700 cubic centimeters. Sorry, centimeters, not meters. The pressure was 200 kPa. And the dP dt was increasing, so that means it's a positive one, of 20 kPa per minute. Okay, so we can reduce this. 20 goes into this guy 10 times, and then 700 divided by 10, or negative 700 divided by 10, will be just negative 70. The kPa units cancel out, so it just ends up being, this is supposed to be cubed, by the way, negative 70 cubic centimeters per minute. So the volume is decreasing, notice because it's negative, at a rate of 70 cubic centimeters per minute. All right, and then the very last one that I had on the video, this one's just one of those that getting the picture correct makes all the difference, so I wanted to walk you through it. It's all about the wording in this problem. So it says at noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? So notice there is this time change of 4 hours there. So when we look at this, the first thing we want to do is kind of draw a picture of the situation. So I kind of imagine a ship A, and ship B is actually going to be, so it's west of this, but it doesn't mean it's directly, because at noon they were directly across from each other, so like this. So B would be here, and it would be 150 kilometers west. But this is going to be a 4-hour time lapse where ship A is moving east, which is this direction, and ship B is going to be moving north. So actually B is going to end up north up here somewhere, because it's heading in this direction. And so when we look at this, so here is the kind of the path of A. It's going this direction, and at one point they were probably on the same line, but now B is going in this direction. So then when we can draw this now, we can measure the distance between A and B by connecting these. So notice we get a right triangle. Now this distance between them, we're just going to call Z. We can call this Y. How far did B travel north? We have to be a little bit more careful with the A, because at this is a change in how we perceive this, because as A is moving, this 150 is changing. Like when we were at noon, it was 150 between these two guys. But because this is 4 hours later, we don't know how far A has actually traveled. It's traveled some unknown distance X. So this is less than 150, but we don't know how much less once we're at 4 p.m. So that's what this picture is representing, which means that before that, A traveled part of the way. So A might have been here originally and B was here, and that was 150 altogether. So we kind of have to be careful when we draw this picture, because there's been a time lapse that we're aware of. And we know that dx dt, essentially, the speed of the A as it traveled along this path so far, was 35 kilometers per hour. We know that dy dt is 25 kilometers per hour. And we want to know how fast is the distance between the ships changing, which means we're looking for dz dt. Okay, So then, because we know that this is not technically our x, we have to just make sure when we plug things in, we're realizing that we're not using x squared in our Pythagorean theorem. We're using this 150 minus x, because this is how much distance would be left between where b used to be and where a is, since it's traveled up to that point. So when I write my formula, it's going to be z squared plus, or sorry, equals, because that's my hypotenuse. The eraser doesn't want to work. There we go. So z squared equals 150 minus x squared plus y squared. So it's still Pythagorean theorem. It's just because of this time lapse that we were already made aware of, we had to describe this part down here a little differently. So then when we take this derivative with respect to time, we get 2z dz dt. We get that this is 2, because I'm going to use my general power rule and then a chain, 150 minus x to the first times a -1, and then it's also got to have that dx dt because it's not actually t, plus, and this would be 2y dy dt. So let's see if we can clean this up a little bit. This is 2z dz dt. This is 300. Actually, I might just leave that factored and just bring the negative to the front. Let's do that. Just trying to make it so it'll be easier to plug into in just a second. So this would be -2 times 150 minus x dx dt. That'll be a little easier to plug into, and then plus 2y dy dt. Okay, so here's the deal. We don't have everything we need yet because we don't have enough information to find dz dt. You have to have every other piece in the problem. So notice I do have dy dt and dx dt, but I don't know anything about x and y specifically themselves. So we need to analyze that based on a formula called distance equals rate times time. So at 4 p.m., because we do know the time lapse, that means that our x, which is this number right here, how far has this actual ship traveled? So remember, this is giving us this, not this number yet. That would be 35 kilometers per hour times 4, because it's been a 4-hour time lapse, so that's 140, which means that our actual side of our triangle is 150 minus 140, which it's 10. So this side right here is 10 now in this specific instance when we've had our 4-hour time lapse. And then y is traveling at 25 kilometers per hour, so that's 25 times 4 hours, so that's 100. So that means this guy is 100. So if we're going to solve specifically to get the z value so that we can plug in everything and solve for dz dt, we have to do Pythagorean theorem. So this is 10 squared plus 100 squared equals z squared, and that would be 100 plus 10,000. So this is z is the square root of 10,100, which I'm probably just going to leave it as it is when we plug it in. We'll just use our calculator for this one. So let's plug in what we know. So we want to plug in 2 times the square root of 10,100, and then that's dz dt. This is -2 times 150 minus the x, which we already know came out as 10. And then dx dt was 35. Plus 2 times y was 100 at that instant, and dy dt was 25. So when we work out this part, so I'm going to go ahead and leave this alone for just a second and work out the right side. That is, let's see, 350 times -2, that's going to be -700. This is 2,500 times 2, so that's going to be 5,000. Then I'll have that dz dt, because I'm going to go ahead and do a couple steps right here since I'm running out of room. 5,000 minus 700 is 4,300. We're going to be dividing that by this 2, square root of 10,100, so 10,100. And you could reduce this down if you wanted to. There's actually, you could pull out a perfect square here, but you're not going to tell someone an answer in terms of square roots usually when it's a word problem like that. So I'm going to go ahead and just work this out all the way to the decimal. So let's type this in. So we have, first of all, let's figure out what that denominator is. So 10, 100 square rooted, and then times by the 2. And then if you have a calculator that has the reciprocal button, this is kind of a neat thing. 1 over x, if you flip that, that'll put that in the denominator since it's right now it's in a numerator. And then we times it by the numerator on top, so 4,300. And I'm getting that that comes out to 21.4 if we round to 1 decimal place. And that would be kilometers per hour. So that is the change in the distance between the two ships as a rate of change of kilometers over passage of time in hours. So like I said, this one's just a little bit trickier just because of the way they worded it. You had to imagine this time passage when you set up your picture. We wanted the picture to represent the at 4 p.m. situation, not at the beginning, because at the beginning, like we said, it looked more like this. A and B are here. There's 150 kilometers between them. This one's going to be heading this way. This one's going to be heading this way. So at noon, the picture was really just a straight segment, but now we've got this distance that they've traveled because they're heading in different directions. All right, so that is the end of the 2.8 video. Hopefully you guys will find this useful when you're practicing your homework problems, when you're studying for your exams. And if you find there's another one that you don't feel like you're comfortable setting up, let me know. I can try to do an extra video on that as well.